data structure problem.
Thanks so much for the invitation. It's great to be here. Thanks you all for coming. Okay, so please feel free to ask questions at any time. My goal is really for you to understand everything, and we're a small group, so if you want me to repeat something or whatever, just please ask. Okay, so this work is called Online List Labeling, Breaking the Log2 Barrier, and these are the authors lined up in alphabetical order: Michael Bender, Alex Conway, Martin Farich-Colton, Hannah Komlush, Bill Kuzmal, and me. And actually half of these people, I'll just point out, are on the job market this season. So besides me, Alex Conway is and Bill Kuzmal is. Okay, so I also should give credit. We made the slides collaboratively, like as a whole group. Okay, so first let me define the problem. So this is the online list labeling problem. And in this problem, what we would like to do is store n elements in an array of size m, where n is about m/2. Just think of n being like a constant fraction of the whole array. And what's happening is that you have an adversary who is inserting and deleting elements from the array. And what we need to do as the algorithm is keep everything in sorted order. So we're required to have everything A, B, D, F, etc. in sorted order. And in order to keep everything in sorted order, we may need to move elements around as the adversary is doing their insertions, deletions. So if the adversary were to insert a C, for example, then we would have to move things around in order to accommodate that. Okay, and our goal is to move around as few items as possible per insertion deletion of the adversary. Okay, so does the problem definition make sense? Okay, so one way to think about this problem, yes.
What's the range of items being?
Oh, that's a good question. So the range of items is actually anything. That is, I could insert as many times as I want in between any two elements. And actually, like, the definition of the problem doesn't even have values in it. It just has, like, the adversary just specifies, I would like to insert an element after the ith element that's present. So one way to think about this problem, like if you wanted to explain it to a child, is you might say, like, imagine you're a librarian and you need to keep all your books in order. And you're inserting and deleting books off the shelf. And you could imagine two different types of libraries you could possibly work in. One would be a library with no gaps between the books, and the other one would be a library that has gaps between the books. And you can imagine if I insert into this library, I'm going to have to move a ton of books around. Whereas if I leave some gaps preemptively, then maybe I won't have to move so much stuff around. Okay, so this problem was first introduced in the 80s. And throughout the 80s and 90s, it was actually rediscovered several different times in several different contexts and given a lot of different names. And these are some of the different places that it was studied. And over the years, it has also found a lot of different applications. So to name a few of them, probably the most well-known one is cache-oblivious B trees. And the result that I'm going to talk about today has, like, an immediate implication for getting better bounds for cache-oblivious B trees. And there's also a whole bunch of other settings that you can get applications for. And you'll notice that some of these papers are in, like, theory conferences, and some of them are in, like, databases conferences and other areas of practice. Okay, so let me now tell you what's known about this problem. So it turns out that from the original paper in 1981 by Itai, Konheim, and Roda, they got an upper bound of log2n. That is to say, whenever the adversary inserts or deletes an element, we are moving around log2n items. It was originally proved in an amortized sense. It was later improved by Willard to be in a worst case sense. From the lower bound side, it's also known from 2013 by Boulinet, Kotsky, and Sachs that you can get a log n lower bound. And so the question that we're asking here is, can we close this gap? What is the correct answer between log n and log2n? So from the upper bound side, since like the 40-ish years since this problem was originally introduced and the upper bound was proved, it has remained unimproved. And from the lower bound side, there have been some results for specific cases. And by specific cases, what I mean is specific classes of algorithms. So if I restrict myself to algorithms that have a particular structure, then I can get some lower bounds. So in order to motivate to you what these specific cases are, let's like take a step back and just think about like, what is the most natural thing you could possibly do to solve this problem? So one natural strategy you could think of would be, okay, we don't want any regions of the array to get too dense. And so when a region of the array gets too dense, I'm just gonna take all those elements that are too densely packed and like spread them out evenly among a larger interval. Okay, so let's say like this, our interval became too dense, then we're just gonna say, okay, we're gonna spread everything out evenly among this larger interval. And you'll notice a couple things about this strategy. One is that it's deterministic if you assume that you're defining too dense deterministically. And the other one is that it is so-called smooth, which means that you're doing evenly spaced rebalances only. That is, whenever the algorithm touches the array, what it's going to do is pick an interval and spread everything completely evenly on that interval. So if we go back to what's known about this problem, it turns out that we know the correct answer for if you restrict to only deterministic algorithms or if you restrict to only smooth algorithms. And in particular, the answer is log squared n. So Dietz, Seyferus, and Zhang have shown that there's a lower bound of log squared n for deterministic algorithms, and Dietz and Zhang have shown a lower bound for smooth algorithms. And so what that means is that when we're trying to answer this question of closing the gap, what we're really asking for is, can we use the power of randomness and uneven rebalancing of elements to improve over log squared n? And in the past, some groups have conjectured that the correct answer for all types of algorithms should be log squared n. And for most of the time that I was working on this problem, I thought that the correct answer should be log squared n. One piece of intuition is that it's kind of difficult to imagine how uneven rebalancing could ever help you, because if you're rebalancing things unevenly, you're creating some sparse areas and some dense areas, and maybe the adversary can just take advantage and insert into the dense areas. So it turns out that that intuition is false, and randomization and uneven rebalancing do help you. Yes.
Maybe just a quick question. So does the adversary see the random choices that you make? Or?
Oh, that's a great point. So it turns out that this lower bound also holds for adaptive adversaries who can see what you're doing. Our only hope is for oblivious adversaries. So we're imagining that the adversary is defining its whole entire sequence of insertions, deletions at the very beginning. So the main result in this work is an algorithm for this problem that has log to the 3/2 n expected cost per insertion deletion. So if we go back to this original picture, now there's a gap between log to the 3/2 and log, and we don't know what the answer is, but we do have an upper bound of log to the 3/2. Yes.
What was exactly the definition of smooth? If you, for example, space them out evenly, but in batches, is this smooth or not smooth?
Oh, you mean like
So,
in batches, you mean like I choose one interval and I spread them out smoothly?
so
and then
let's
I
say
choose
that
another?
I take one interval and I want to spread them out smoothly, but instead of putting one element in each like same distance, I want to put like, I don't know, several elements in same.
Oh, you put them sort of in blocks, like you put maybe 3 clustered together
Yes,
and then a
but
gap.
still in same distances from each other.
I see. This lower bound only held like for strictly smooth, where you spread everything out exactly evenly. Yeah, that's a good point. If I had to guess, I would think that the batching thing could also maybe extend to their lower bound, but I don't know. It's a good question. Okay, so the upper bound of log to the 3/2 n, you'll recall by necessity has to be both randomized and non-smooth. So let me now give a couple of observations that I find interesting about this result. One is that it turns out that randomization and uneven rebalancing only help when your array is of a particular size. So when your array is like linear in the number of elements that are in the array, you get this benefit. On the other hand, it was already previously known that when your array is much bigger, let's say your array is like polynomial in the number of elements that are in the array, then we know that log n is the correct answer, and the algorithm that realizes it is both deterministic and smooth.
Is it hard to see the upper bound?
You mean the upper bound of log n? So in a bit, I'll show you the classical algorithm for this problem, which achieves log squared n for the linear case. And it turns out that also achieves log n for the, so you'll basically see how it works, but like the parameter that we choose will be different. But besides that, it'll just work. And the second thing you might think is when you first see this number, you might think, you know, isn't log to the 3/2 n kind of an unusual number? And maybe if we can break log squared n, we can probably get all the way down to log. It turns out that there's at least some evidence to believe that maybe log to the 3/2 n could be the correct answer. And that evidence comes in the form of saying, well, it turns out that actually log to the 3/2 n is tight for a particular natural class of algorithms. So let me now tell you about what this class of algorithms is. So this class of algorithms is what is called history independent. And the idea of history independence is going to be one of like the very main ideas of this whole talk. So the definition of it will be very important. So the definition of a history independent algorithm is that the current state of the data structure reveals nothing about the history of past operations that the adversary did. Except you can see the items that are currently present, but beyond that, I have no idea what order the adversary inserted them in, what insertions and deletions happened along the way. And this is a concept that has been widely studied in a number of different data structures. And usually the goal of this type of work is to say, okay, we have a data structure that we like, and we would like to add an additional nice property to it, the property of history independence. And so the question is like, can I match the state of the art for this data structure and also have the nice property that it's history independent? Okay, so that's how history independence has been studied in the past and the definition. And now let me zoom in. Yes.
Is that going to be like with high probability, or is that like all
the definition of history independence?
right? Like if it's a randomized algorithm?
Oh, right. Yes. So let me say the definition for list labeling, and then I think this question will be clear. So for list labeling, the definition of history independence is that the distribution of occupied slots, and this distribution is based on the randomness of the algorithm, the distribution of occupied slots depends only on the number of elements currently present. So if I have 10 elements in my array, I immediately know the distribution of all the slots that could be occupied. If I have 20, it's some other distribution, and I immediately know that. And you'll notice, this is kind of a caveat of the definition of the problem that was from your question earlier, that we're only depending on the number of elements present. Like I'm not even talking about the identity of the elements. And the reason for that is that the elements don't really have values because you're just inserting based on like, what is the index? So then caveat is over. So to reiterate what this means for list labeling is that if I have these two different arrays that have like different identities of the elements, it should be that you'll see that like the occupied slots are matched up. And it's not that they have to be completely matched up, it's just that the distribution has to be the same. And it also has to be the same regardless of what I did in the past. Okay, so is that definition okay of history independence? Okay, so what we show in this work is in particular that the upper bound of log to the 3/2 n is history independent. And then we also show a matching lower bound of log to the 3/2 n for the specific class of history independent algorithms. That is to say, if you restrict only to history independent algorithms, then we know that log to the 3/2 n is the correct answer. It turns out that history independence has been studied previously in the context of list labeling, and they got a log squared n algorithm. That is, they matched the state of the art at that point in time, and also had the property of being history independent by this set of authors in 2016. Okay, so one way to think about this talk is even like not specifically for the list labeling problem, but just kind of like a proof of concept that you can actually kind of use history independence as a tool in upper bounds. And this brings me to kind of like the one key point of this talk that I want to say, which is the following. So previously, history independence was viewed as a desirable property to achieve in its own right, like for some kind of security guarantees. If an adversary looks at the state of the data structure and doesn't get any information about what happened in the past. On the other hand, we kind of use this property to achieve, like as a tool to get a faster algorithm. And this is the one main point that I want to get across.
I
Yes.
actually think that the original proof that linear hashing works was also basically using this.
Okay,
And the way
interesting.
that the proof works is that showing that deleting an item reverses the state of the hash to what happened if this item was never inserted. And this is the way that analysis with only insertions is translated to the general case.
Okay, interesting. So maybe we're not the first ones to
It's
to
maybe
use
not
history
exactly the same
independence.
type of history independence because the order does matter, just showing that deletions are equivalent to never inserting an item and then saying that you don't need to analyze what happens after deletions because of that.
Oh, I see, but it still can depend on the order
It can
of
depend on the order.
insertions. I see. Interesting.
So hashing with linear probing.
Yes,
Yeah,
so
okay.
check it like in our program is, I mean, this is the original analysis.
Okay, so the key point is that this work can be viewed as kind of like a proof of concept that history independence can be useful in upper bounds. And let me just say some high-level words about why this concept can be useful in upper bounds before getting into any details. So this is kind of a preview of what is happening later. So so the question is, why is history independence useful in an upper bound? And the short answer to this is that history independence is all about hiding information from an adversary. And so if we look at these two different ways history independence has been used, we can first look at the one from prior work. And the one from prior work is saying, okay, by observing the state of the data structure, the adversary can't know anything about what happened in the past. And this is the kind of security guarantee that we want. On the other hand, when you use history independence for the purpose of speed, we're kind of reversing the order of things here. And we're saying, okay, by knowing the history of insertions, deletions, the adversary can't know anything about the current state of the data structure. Of course, the adversary knows the whole history of insertions, deletions, because they're the one who defines it. But we're saying no matter what the adversary chooses to do, what order, they can't know anything about the current state of the data structure because it only depends on the number of items present. And that somehow allows us to kind of fool the adversary because the adversary can't take advantage of the current state of the data structure and just, let's say, only insert in dense regions or something like that.
But still an oblivious adversary that has to do it in advance, or like, I'm just a little confused. I think you said it was against an oblivious adversary.
Yes, it's
right?
against an oblivious adversary.
Yeah, okay. I think I'm just a little confused with knowing the history, but if it's oblivious and anyways have to do it in the beginning. So what does it mean, like not knowing the state of it?
Right, so like, okay, I think I see what you're asking. So like, you could imagine a situation where the adversary knows the algorithm, the adversary knows what the algorithm is going to do. So the adversary, even if they're defining everything ahead of time, they could say, okay, at this point in time, I roughly know what the algorithm is going, what the array is going to look like. And because of that, I can like take advantage of it.
I'm not sure, so yes, based on history independence, like adversary don't get much information, but on the other hand, maybe like if it's history dependent, then maybe still like the entropy is larger than the history independent case. So I mean yes, indeed, the adversary may learn something from history dependent case, but the remaining entropy is still a lot larger.
Sure, yes. As in you're saying like it's not actually clear that history independence will help you because the adversary can still know something, like they still know the distribution if I have 10 items or something, and maybe they could take advantage of that. Yeah.
So the case where the adversary is allowed to be non-oblivious, what's the situation there?
So log squared n is the correct answer. You can get a lower bound. Okay, so now I'm gonna get into some details of telling you how stuff actually works. So the rest of this talk will be the log to the 3/2 n algorithm. I have some extra slides at the end about the lower bound if you still have energy or time by then, but let's say the main goal is to talk about the algorithm. Okay, so in order to talk about the algorithm, we first need to talk about the classical solution from 1981. And then we'll try to kind of modify what's going on with the classical solution to get a better bound.
Just before you go into just one more question. So what happens if the adversary does its actions at random?
Oh, that's a great question. So it was previously known that if the adversary does the actions at random, it's actually you can actually get a constant number of items moved around.
I'm confused about if the adversary is stronger. Sorry, this is a basic question. Then you get the tight lower bound, but that upper bound is log to 3,000.
Can you repeat the question?
Why doesn't this log squared lower bound contradict this upper bound?
Oh, the log squared lower bound is only for deterministic algorithms or algorithms with an adaptive adversary. But this is algorithms with, this is when you have an oblivious adversary.
So the lower bound that you have is log to 3/2 n. That's for any kind of adversary, as long as it obeys these two conditions. As long as it's, so you have a log to 3/2 n lower bound
For history independent algorithms, yes.
if the adversary can be of any type.
What's an oblivious adversary? I guess it's an oblivious adversary at the low bound. An oblivious adversary against a history independent.
That's so confusing. Anyway, I think we could just.
Yes. Yes, so I mean, if the adversary is if it's already deterministic or adaptive, we already have log squared n. So the place where the history independent lower bound actually means something is when the adversary is oblivious. But did it answer? Because is there still some?
I think I'm okay. No, yeah. It's
Okay. Okay, so for the classical algorithm, the way it works is the following. So what they first do is partition the array into nested intervals. So this top interval represents the entire array. The next one is now split into 2, and then we have 4 intervals, etc. And they maintain a particular invariant about these intervals. And the invariant that they maintain is the following. It's an invariant about the density of a child interval with respect to its parent interval. And the density of an interval is simply just the number of items that are in that interval divided by the total number of slots in that interval. Okay, so what this is saying is that the ratio of the density of the child to the density of the parent can't be too big. They can't be too different. They can only differ by like a 1 over log n So in particular, you could imagine that, so we have the density of this particular parent interval, and what we're saying cannot happen is, like, let's say this interval is very dense and this one is very sparse. Both of them should be like roughly equal to the density of the parent interval. Okay, so what I would like to now convince you of is that if you can get an algorithm that maintains this invariant, then you have a valid solution for the list labeling problem. So in particular, we can analyze the densities of all the different intervals as we go down. So we know that the density at the top is just constant by the definition of the problem. And then we can consider, okay, what's the densest possible thing that the density that the child could have? Well, it's gonna be like the original density times a 1 plus 1 over log, just from the definition of the invariant. And then you can imagine that as we go down, we can get another one of these 1 plus 1 over log factors until we get to the bottom. And the point is just that once you get to the bottom of these log n levels, your density is going to be like 1 plus 1 over log n all raised to the log n. And because this is a constant, we don't experience overflow. That is to say, there's always enough slots for the number of items we want to put in. It's never the case that we have only 10 slots and we want to put 15 items into those slots. Okay, so this is just saying that this is, if we can maintain this invariant, then we're good. So now I need to tell you how to actually maintain this invariant. And what we do is something very simple, which is just when the invariant is violated, we're just gonna spread all the items evenly out over the parent interval. So let's say this interval violates the invariant, which means that like this part of the array is much denser than the parent interval of the array. And so we need to spread out these items. And what we're going to do is just say, okay, take the whole parent interval and spread all these items evenly. And that's the entire algorithm. When the invariant is violated, just spread everything out evenly. And this is when the invariant is violated for any interval at any level of the tree. Okay, so before I tell you why this gives log squared n, let me kind of belabor this algorithm by saying it in a different way. And the reason I want to do this is because later we're going to see a variant of this algorithm, and it will be useful to like talk about it in slightly different language. So the invariant I'm now going to phrase in a slightly different way, and I'm going to phrase it as something called, with respect to something called the pivot. And the pivot of an interval is simply just the item that appears right in the middle of the interval. So if I'm talking about this whole entire interval, like the top one, the pivot is just simply the item that appears like J right in the middle. For this interval, the pivot is T, let's
So
say.
you mean like, you don't mean that there's half the left and half to the right, you mean.
I don't mean the median, I mean like literally at this point. So it could be empty, like the slot could be empty and there could be no pivot, but if there's an item there, then we're going to call it the pivot. And what we would like to say is that the pivot of each interval falls in the middle, 1 over log n fraction of the elements around the median of all the elements that are in that interval. And this is just like the same thing as saying that density of parent versus density of child thing, because we're saying that, you know, if the pivot, which falls right in the middle, is within like the middle 1 over log n fraction of the elements around the median, then you get, then you cannot have it be the case that one side is extremely dense and the other side is extremely sparse. So let's now verify that this particular array configuration is valid according to this invariant. And so in particular, let's say we first look at the pivot of the top interval, which is this J, and then we say, okay, let's look at this particular candidate set of 1 over log n fraction of elements around the median. The pivot falls into that set, and so we're happy. And then we can like continue verifying that the pivot is indeed in the candidate set as we go down the tree. Is that all okay? Yes.
Is the bottom level of the tree of batches of size log of something? I mean, how do you maintain a variant in small things?
Yeah, that's a great question. Yes, it is log. Yes. Okay, so now we can imagine, now we need to like do something that's going to violate the invariant. So let's say we insert this element P, and then we say, okay, let's go down the tree. That pivot is still valid. And this side of the whole, this side has not changed at all because we didn't insert into it. But now this side now violates the invariant because the pivot is this element Q and it doesn't fall close enough to the middle here. And so then we need to do this rebuilding situation where we now recursively rebuild this thing, which is the same thing that we did before in the other description of the algorithm. And the point is that we're now going to recursively select the median as the pivot in order to basically spread everything out evenly. Okay, is that all okay? Okay, so now I'll tell you where the two log factors come from. Why does this give you log squared n? So one of the two log factors comes from the fact that there are log n levels of this tree. And the second log factor comes from the cost of doing this rebuild thing. Okay, so in particular, if we rebuild an interval of size s, then I'm claiming that actually required us to do s over log n insertions, deletions to that interval before we had to rebuild it. So imagine we just rebuilt an interval, we set the pivot as the median, and then we're asking how many insertions, deletions do you need into this interval in order to push the pivot out of the candidate set, which is a 1 over log n fraction of the elements. Well, we need a 1 over log n fraction of the elements to be inserted into this interval. And so that's s over log n insertions, deletions. And so what that means is that at the end, our cost is going to be s for, that's the cost of a rebuild, because when we rebuild an interval, it's of size s, we're paying s, but we only do that once every s over log n insertions, deletions. And so we get log n. So in the end, we have these two sources of log n's and we get log squared n. So now we need to try to make this algorithm better. And the way that we're going to do that is kind of in a couple of iterative steps where we say, okay, here's an idea, here's why it fails, let's try to fix it, etc. So the first idea is going to be something very simple, which is, let's just balance everything less tightly. Like that is to say, let's have our candidate set sizes for the pivots be larger, because what that would mean is that it would take a longer time for the pivot to actually get out of the candidate set, and then we'd have to just rebuild less often. Okay, so that is to say, we would like to have a new invariant. And I'm going back to the density version of the invariant, but you could also think of it as the pivot version. And let's say we have this new invariant which says, instead of the density child parent ratio being 1 plus 1 over log n, it's now going to be 1 plus like 1 over square root log n. Let's forget about like log factors in the O tilde. Okay, so if we were able to do this, we could say, okay, now the cost of maintaining the invariant by the same calculations on the previous slide would be square root log n. And then at the end, we would get a final cost of log to the 3/2 n, which is what we want. So this would be very nice if we could do this, but the problem is that it doesn't work. And the reason it doesn't work is because some intervals might overflow. So what I mean by that is the following. So you'll remember this exact picture from before where we were saying, if we could maintain that invariant with 1 over log n, then you'd never experience any overflow and there's enough elements at the bottom. But if we change this to square root log n, like I change this to square root log n, all of these become square root log n, here's a square root log n. My density at the end is going to be 1 plus 1 over square root log n, all raised to the log n. And then this is going to be super constant, and so there's not even enough slots for the items, and this is not even like a valid algorithm in the first place. Okay, so we would really like to be able to still use this idea, but we need to take care of the situation that things are overflowing and we don't have enough slots in the array. So that's where the second idea comes in, which is that we need to have a way of like handling dense regions, that is regions that are at risk of overflowing. And what I first want to claim with these dense regions is that actually there's not too many of them, and that's going to then help us in the future. So what I first want to claim is that yes, while we do experience overflow, like not too many intervals overflow. So in particular, I'm claiming that at most a 1 over polylog n fraction of the intervals experience this overflow. So now let me convince you of this point. And the idea of how you prove this point is, let's say we chose a random sequence of nested intervals. So we chose all of these, we chose one at each level and they're all nested and we chose them randomly. And then we can figure out what is the expected density that we're going to have. And you'll notice that the densities form a random walk. So at the beginning, the density is some constant and then we know that the density on one side and the density on the other side are, their average is the density of the parent interval. So we know that it's an unbiased random walk. And we're just choosing with 50% chance, do we take a positive step or do we take a negative step? The step size might be anything from 0 to 1 over square root log n, because that was our invariant of the density differences. So our step size is anything between 0 and 1 over square root log n, and we take this random walk all the way down to the bottom. And then we ask ourselves, what is the density at the bottom? And we can use this fact from random walks that if I take k steps of a random walk, I'm going to probably be at distance about square root k from the origin. And so let's see what that gives us here. We're taking log n steps of the random walk, so we're expected to be like square root log n distance from the origin. And our step size is at most 1 over square root log n. And so these square root log n's cancel each other out. So in particular, with high probability at the end, if we consider the density of the interval on the bottom, we have that it is square root log n, because that's from the random walk, square root k, log n steps of random walk, getting square root log n. And then this is the step size, 1 over square root log n, and then that gives us a constant. And so we're saying, with high probability, we do not experience overflow.
High probability is 1 minus 1 over polylog, right? Not 1 over poly n.
Yes, because the number of it should be high probability with respect to the number of steps in the random walk, which is log n, and that's why we get this 1 over polylog n. So now we're in a situation where we don't have too many dense spots in the array, but we still have some and we still have to deal with them for it to even be a valid algorithm in the first place. And so how do we deal with these dense spots? Well, we're just going to revert back to the original log squared n algorithm. Okay, so whenever an interval gets too dense, let's say it has like 9/10 of its slots are filled with like 9/10 of the slots are filled with elements, then we just revert back to the original log squared n solution. And so now we actually do have a valid algorithm, and this algorithm has the following guarantees. So if you think of this as the array, and the blue regions are kind of the sparse regions, and then the red regions are the dense regions, what we know is that the red regions that are dense only consist
What
of...
exactly does it mean to reverse? I mean, aren't you doing the same thing just with different thresholds?
Exactly, yes.
So what exactly are you doing? Are you changing the threshold for the future in this interval or for now?
Yeah, I'm changing it for now, and if it becomes sparse again, then I'll go back to the old version.
I don't fully understand that. because you're on the way you describe your algorithm, you basically have a threshold for density in which you are uniformizing stuff. You are saying that if this density gets too high, then you are doing this thing. So
like, I'm not sure if this answers, but
I'm trying to understand what is the difference between the cases actually. What is that?
what is the difference between like the dense case and the sparse case?
Yes, like what do you see? What is the criteria to decide that now I take everything in my interval, making this uniform?
Right, so the criteria will be like the invariants from before. So this would be the invariant of like the density of the child versus the parent.
Sure.
So by default, our invariant is that we need them to be like within 1 over square root log n from each other. But then we're saying if the density becomes too big, then we need them to be within 1 plus 1 over log n of each other.
We tried something smoother. So currently you're kind of cutting at 2 different places.
Yes.
So
Yes.
you're not getting anything better.
Yes, that's a great point. So it turns out that just by using one threshold, you can get log to the 3/2 n with some extra log factors, but you can get rid of those log factors by doing the smooth thing that you said. And like the way it's written in the paper is the smooth thing.
When you say smooth thing, you mean?
I mean, a whole bunch of different sparsities. So like instead of just having sparse and dense, we have like all the different levels of.
What do you do?
They have 2 different cutoffs here. One is 1 over root log n, one is 1 over log n. But you
Yes.
can do 1 over log n to 3/4 to
Right, but how do you decide?
7/8.
You decide based on how dense it is. So here we're saying like, if you have a sparse interval, you do 1 over square root log n. If you have a dense interval, you do 1 over log n. But instead in the smooth situation, we'd be having a bunch of different sparsity cutoffs. And we'd say, if you're on like the ith sparsity cutoff, then your like density threat thing is like somewhere in between 1 plus 1 over square root log n and 1 plus 1 over log n. Okay, so we're now in the situation where the vast majority of our array has a log to the 3/2 cost. That is, if the adversary chooses to insert here, it's going to be log to the 3/2. But there's a few dense spots where if the adversary chooses to insert here, it's going to be log squared n. And for this reason, we're still vulnerable to the adversary. That is, if the adversary knows where these dense spots are, they can just keep on inserting into there over and over again, and the final solution will turn out to be log squared n, and we haven't made any progress whatsoever. So now what we need to figure out how to do is to kind of hide these dense regions from the adversary. Okay, so the way that we're going to hide these dense regions from the adversary is using the power of randomization and this idea from before of history independence. So let's zoom in on what the real problems are here. So it turns out there's like 2 distinct problems, and both of these distinct problems result in the adversary having some information about where the dense places in the array are. So one of the problems is that the adversary can actually create dense regions, right? If the adversary like inserts over and over again at one particular region, and the algorithm does not do enough work in spreading that stuff out, then the adversary has some control over where the dense regions are in the first place. The other problem is that the adversary can find dense regions, even if the adversary did not create them in the first place. So what number 2 is saying is, let's say the adversary has some knowledge of how the algorithm works, and the adversary knows that the algorithm is going to be more likely to create a dense area and this particular location, then the adversary can take advantage of that. So the first one is adversary is creating dense regions, and the second one is adversary is finding dense regions that were created by the algorithm.
I'm not sure I understand 2 at all, because I guess you haven't described the. Yeah, I don't understand how the algorithm can create dense regions without the adversary. It depends on the choice of.
Yeah, so I'm not saying in particular that the algorithm that I just told you about creates dense regions. I'm saying, like, in general, you could imagine that some algorithm that you're talking about could be like more likely to concentrate a lot of elements around index 10 or whatever. Like, that's something that an algorithm could potentially do. And like you said, it's not clear that the actual algorithm that we're using from before does create these dense regions. And it turns out that this one is like, the fix for this one might actually not be necessary for that reason, but it's kind of like makes things more simple if we just kind of fix it. Yeah. Okay, so let's first focus on the first problem. The solution is history independence. And let me tell you why the solution is history independence. And so the question that we're asking is, why does history independence prevent the adversary from creating dense regions? And the answer to this question is basically just like by the definition of history independence, because you'll recall that in the definition of history independence, the distribution of slots depends only on the number of elements currently present, meaning that the adversary can't like do something really clever and insert things in a particular order and expect to create dense regions. No, the dense regions are only based on the number of elements currently present. And so the adversary basically has no hand. Whatever the adversary does in the past, is like completely independent of the structure of the current array. So what this is saying so far is like, if we were able to have an algorithm that had the property of history independence, then we would be happy and we would not have this problem where the adversary can create dense regions. I haven't told you how you actually achieve history independence. We're just saying if you can get something that's history independent, then we're good. Okay, so now for the second problem. The adversary can find dense regions that the algorithm may have created. And it turns out the solution to this one is also basically history independence. And we also use this extra ingredient called the random shift. And like I mentioned before, the random shift might actually not be necessary. Maybe you could have a different analysis of this algorithm, but it kind of just makes things easier to analyze. Usually I think of this as more of a technical detail, and if I were giving a talk that wasn't as long as this one, I would just kind of skip over it. But because you're here for the long haul, I'll tell you more about how this random shift thing works. So the way that it works is that at the beginning of the algorithm, we're going to insert n dummy elements. So like we have n elements here, so we have like 4 real elements, and we also have 4 dummy elements. And then we give these dummy elements and these real elements to the algorithm, and the algorithm puts them in some particular places in the array. And in particular, out of our n dummy elements, we're going to put a random number of them at the beginning. That is to say, we give them like value -infinity or something, and then we put the rest of them at the end. So what that means is that like the real elements that the adversary is talking about are kind of like at a random position somewhere in the array. And so the intuition for why this helps is that, like, let's say the adversary inserted between D and H, and it successfully hit a dense region here. But on the other hand, if we had just taken a different random choice of how many of the dummy elements to put at the beginning and how many to put at the end, let's say we put all 4 of them at the end, then the same exact insertion between D and H would be a good insertion for us, and we could just put it straight in there. It's not a dense region. So that is to say, we're kind of hiding the dense regions from the adversary by making it equally likely that they're going to be somewhere in the array, depending on like how many of the dummy elements we chose to put at the beginning and the end.
I'm confused just a little bit. Like, wouldn't you expect them still rather close? Like the dense regions don't change too much. Like it's not by n that they move, so they don't move all over. It's more like Udon or something to a certain cell.
We're imagining that we have inserted n. We have like the same number of dummy elements as we have real elements.
Yeah, doesn't that only shifts? Like, how do you choose how many goes first and how many goes last?
We choose it like uniform random from 1 to n.
Okay, yeah, sure. Sorry.
Is it equivalent of, as if thinking that your array wraps around and then you just choose where is your starting point, right?
Yes, I think it should be exactly equivalent to that.
I think I was thinking about tossing a coin for each of them to decide which side, but that doesn't work, right? Because you're almost always at in half roughly, but of course you just choose.
Oh, I see what you mean.
Yeah.
Oh, yes, good point. Okay, so the point is that since most of the array is sparse, the adversary is unlikely to kind of get lucky and hit a dense spot. And in particular, we've like converted an adversarial insertion at rank k. And what rank means is like
exactly is what are the operations? Do I insert an element that is comparable to the others with like a certain key? Or
you mean like how are the dummy elements defined?
no, how are the operations of the entire like data structure defined? I'm trying to figure out the following thing. If I'm inserting elements that are comparable to each other, then wouldn't their order with respect to each other remain the same regardless of these dummy elements?
Yes. As in the order of the true real elements the adversary inserted, those should be the same.
Yes. So you would want to say that somehow it's not. So it's not that the shift helps me because I'm now pointing at some weird random location. I'm still pointing at the same location with respect to all of the non-dummy elements.
Yes.
But still somehow moving all of them is enough to get me away from the bad locations.
Yes. And actually, the reason for that, which I think I forgot to mention, comes down to history independence. This random shift thing only works for a history independent algorithm because we're saying like previously, like if you look at the array slots that are full here, it's something, but then if we actually put the more dummy elements at the end, we're still considering like the same array slots being full.
So you're saying that because of the history independence, now even though I am at the same spot with respect to the real things, it is exactly equivalent to just being the ith element, which is now a random number between.
Yes, that's exactly right.
Thanks.
Okay, so we have these two problems and both of them are essentially fixed by the idea of history independence. And so now we need an algorithm that is actually history independent. And the fortunate thing for us is that there is a previously known history independent algorithm that achieves log squared n. And we're going to use this algorithm. And we're not going to use it as a black box. We need to look inside of it, but it's actually quite simple and quite similar to the classical algorithm. So basically everything we've talked about in the past will also be able to be squinted out a little bit and basically apply for this algorithm instead of the classical algorithm. Okay, so the way that, now let me just tell you the way their log squared n history independent algorithm works. And the way that it works is that it's the same as the classical algorithm, except instead, you'll recall that we picked whenever we did a rebuild in the classical algorithm, we picked the median as the pivot. Now we're going to pick a random pivot from the candidate set uniformly at random. And we're going to have that be the invariant. So so for every interval, we have our candidate set of pivot choices. And our invariant is going to be that the pivot is a uniform random choice within this set. And so what that means is that if, let's say, another element gets added to the pivot candidate set, even if your original pivot didn't leave the pivot candidate set, we still need to do some resampling to make sure everything is uniform. And to do that, we use reservoir sampling. That is to say, let's say I have 10 elements in my pivot candidate set and another one gets added, then I just sample this new element with probability like 1/11, so that everything is still uniform. And so what that means is that like we might need to rebuild even when the pivot is still in the candidate set. So just to give a picture, to help you visualize what's happening here, our invariant is that, okay, so this is all the elements in this interval, and this is the pivot candidate set, which is defined as the middle 1/log(n) fraction of elements that are in that interval. And what we're saying is that I'm choosing one of these uniformly at random to be the pivot, and I'm doing that like recursively. And again, let's say Q was added to the pivot candidate set. Now I would sample it as the pivot with probability 1/4 so that everything remains uniform. So does the definition make sense? So if you think about it for a bit, you can figure out why this is actually history independent. So what you should be imagining here is like, I give you the number of elements that are in the array. Let's say there's 20 elements in the array, and you should be able to immediately tell me what is the distribution over where these elements are located in the array. And the reason that I can do this is because I have this special invariant, which is saying that the pivot is chosen uniformly from the candidate set. So without knowing any of the history, I can just tell you the distribution by saying, okay, look at all of the elements on the top interval, look at the pivot candidate set, pick one randomly, go to the next and go do that recursively, always be picking one randomly. And that gives you the distribution of where the elements are.
So could you say that again? Just a little bit faster.
Yes.
So you put them all in the beginning, like there at the bottom. Or, yeah, what's the top?
Right, okay, so what we're trying to prove is that this algorithm is history independent. And so what that would mean is that if you tell me the number of elements in the array, like you tell me there's 20 elements in the array, I can immediately tell you what is the distribution of like where these elements are actually located. Yes, so the distribution is given by the following process, where in the process we start with the top interval, which means that we're considering all of the elements in the whole entire array. And then we look at the pivot candidate set, the like blue box, which will be around the median. We pick one randomly, and then we divide based on that into the two sides. So now we have some elements here and some elements in that interval. And then again, we recursively pick someone from the pivot candidate set as we go down the tree.
It's just a little strange to me that you pick the region around it to fixed size, equal probability, and that doesn't.
And that doesn't violate history independence?
Well, don't you eventually want that the bad spots are like uniformly distributed? Like the bad places are, maybe I have in my head what you were going to do. So like the distribution of two dense places, what does it look like? It's not uniform, is it?
Well, okay, so I think what you're getting at is the point, what's the point of the random shift? Because maybe the distribution of dense spots, maybe it isn't uniform. Maybe it's more likely to be dense in some places than others. But the point is that like the random shift idea should fix this.
I would have thought to do something like pick something to be the pivot proportional to its distance from.
Maybe that would also work. Yeah, like that would still be history independent.
I'm trying to get some intuition about why does the shift do anything, in the sense that after the shift, if I'm playing with the rest of the elements and roughly keep the same number of them, And it looks like there would be some subtree in which everything looks as if I didn't have the dummy elements at all. Why is that not true?
Can you say that one more time?
Yes, I'm saying the following thing. Let's say that I inserted the dummy elements like with your random shift. Now I'm inserting like, I don't know, another n/4 elements or something like this. So the dummy elements are n, I'm inserting a bit less than that. And I will keep now I will do insertions and deletions, we'll keep the number of elements roughly n/4, like for the entire time. So it looks like I will have some subtree, like some interval in which most of my elements are going to fall in.
Yes.
And now whatever I'm going to do is not really going to be affected by the random shift, right? Because it will look like as if all of this is in
Yes.
some.
You do the random shift just once at the beginning. And
Yes.
yes, so that's right.
But also the points in which I'm going to do the new operations are always going to be within this same subtree that is not affected by the shift.
Yes.
So how does the shift still help?
Well, the point is that the shift still helps because without the shift, the adversary might be able to predict which regions of the array are dense. Because I don't know, maybe this algorithm has the property that it's more likely to be dense like in the middle than on the edges or something. I don't know. And because of that, the adversary might be able to predict that. But with the random shift, like we're now shifting, we don't know if we're in the middle of the tree or on
I
the
guess
side.
what I'm trying to say is that I can't currently see a reason for if this is true with the shift, for why it wouldn't be true without the shift.
So it might be true without the shift. The shift might be unnecessary, but it made the analysis easier.
Thanks.
Okay, so this is how the log squared n history independent algorithm works. And now we just kind of need to integrate all the pieces together into the final algorithm. So let me list all of the ingredients that you've already heard. So one of them is, of course, the history independent log squared n algorithm. And then we're combining this with the random shift, and we're combining this with the idea of enlarging the candidate set size of the pivot, as in the original history independent algorithm was a 1/log n fraction of the elements in the interval. And now we're increasing it to a 1/√log n fraction of the elements, just like we did before. And this speeds up the algorithm because it means that the pivot is going to move out of the candidate set less often. We have to rebuild less often. But then this comes with a problem that you might experience overflow. And then in order to not have this overflow, we again revert back to the smaller candidate set size, which is a 1/log n fraction of the elements, particularly if a region gets too dense. And then these four ingredients give you a log⁵n algorithm, also with some log factors. And like you mentioned earlier, you can also smoothly vary between the candidate set sizes and the densities in order to get down to actually log⁵n. So let me now, this is like where I would usually kind of end, but let me now just make things more concrete for you since we have a bit of time. Like just to show you exactly how these things all combine together and give you an algorithm. So the actual definition of the algorithm is the following. So up above, we have these two invariants, and I'm ignoring the smooth stuff. This is for the O tilde version. So down here, we have the algorithm definition, and up here we have the invariants. So we have these two invariants, one for the dense intervals and one for the sparse intervals. So the invariant for sparse intervals is saying like, okay, let's say it's for density like less than 9/10 or something. The invariant is that the pivot is a uniform random element of the middle 1/log to the square root fraction of the elements around the median. And then we have this different invariant for the dense intervals where we're saying that the pivot is the uniform random element around the 1/log n fraction of the elements around the median. So we have these two different invariants. And then how do we maintain these invariants? First, there's like the pre-processing step where you do the random shift of inserting n dummy elements with a random number at the beginning and a random number at the end. Might not be necessary. And then we have the algorithm for insertion deletion, which is simply that we scan the tree of intervals from top to bottom. So we consider the whole interval of elements, then down to half, etc. And if the pivot candidate set has changed based on our insertion deletion, the pivot candidate set might have lost or gained an element. And we need to keep the invariant that the pivot is a uniform random element of the candidate set. So then we just resample using reservoir sampling to resample the pivot down the tree.
I don't know what that is. Is it
Reservoir sampling? Okay, so this is the idea from before where like if I have 10 elements in the pivot candidate set and I add an 11th, out of my 10, I already have something sampled, uniformly random out of the 10. And if I add an 11th element, I just sample that additional element with probability 1/11.
Even if you pick that one, you override the other one?
Yes. Yes.
I guess there's some taken care of. If the pivot moved out of the candidate set, the one that you were maintaining already, I guess then you have to resample again. Right?
Then you have to resample uniformly, yes. Okay, so this is the way that the algorithm works. And now if you don't have more comments and questions, I'll just move on to stating like the open problems that we have now. So we have a new open problem, which is closing the gap between log to the 3/2 n and log n. We don't know what the correct answer is. And, there's a few reasons to believe it might be one over the other. If the correct answer is that you can get below log to the 3/2 n, we know that you need to give up the property of history independence. That is to say, if you can get a less than log to the 3/2 n algorithm, it has to have several different properties. That has to be randomized, non-smooth, do uneven rebalancing, and be history dependent. On the other hand, maybe this like history independent lower bound that we have like extends to all types of algorithms. We don't know. Okay, so maybe history independence is the correct answer because it hides information from the adversary effectively, but maybe it's not the correct answer because it seems kind of expensive to maintain it or something. So this is like the main question. And actually, there's also a question which is not up here, which is that this is only amortized, and it would be equal to get it for worst case as well. And then there's this kind of more general.
So many things. This is like for amortized algorithms with randomization.
Yes.
How much does the lower bound, sorry, I don't remember from Monique. How much does the lower bound use the really strict definition of history independence as opposed to like a relaxed version that would be?
It uses the strict definition, and it's like unclear how to use a more relaxed definition. So a second question looking forward is like more generally, we used this concept of history independence to get a faster algorithm. And so you might imagine that there could be maybe some other data structures out there that would benefit from being looked at in a history independent way in order to improve algorithms. And that's it. I have a few more things on the lower bound if you like have energy, but let's say that's it.
I guess when the density of the three elements to the size of the set, that's just, you just do the strip that you have with 1 plus 1 over square root. Or, anyways, you can make that denser and get all the way to the bottom. Is the point?
Can you repeat that?
So at the beginning, you said that if the the size of the array is significantly bigger than the size of the set.
Oh, like if it's
Just change the parameters. Like if it was n to the 1 plus
Yes, if it was like polynomial in the number of
So then you
elements.
can just do, then you can be much denser. And
Yes, then your candidate set size can be such that you're like paying a constant. So
I think I understand.
yeah, it can be a constant fraction of the interval. Yes.
What's that little and I mean, like when exactly that yeah, we don't need this log n overhead. Just following Tony's question, I wonder like for the constant overhead, what is exactly the size of the array?
For the constant over, can you repeat it one more time?
Okay. If we don't want this log n overhead of log n square overhead at all, how much the array should be?
Oh, are you talking about like the threshold between
Yes,
the
yes.
linear thing and the
Yes,
polynomial
yes.
thing? I see. So what we prove is, I see. So yes, one of the things that we proved in the paper is that you can get kind of a smooth transition between the sparse case and the dense case. So the answer to your question is that there is a smooth transition, and I don't remember the exact parameter.
But for example, if it's n squared,
Then it should be logging.
Oh, if it's n squared, yeah, if it's like if it's n to like 1 plus epsilon for constant epsilon, then it should be log squared, I believe. And the transition is only for the like the part in between when it's less than that.
So can you say a few words about how you use the shift in the proof?
Right, okay, so the shift is saying, the shift is like presented as a reduction from the case where you are choosing your rank to insert in randomly versus when it's chosen adversarially. So by doing the shift, we're saying that we're like transforming an adversarial insertion at rank k to a random insertion where the rank is somewhere between k and k plus n. So that's what the random shift accomplishes. And then for the rest of for like the majority of the paper, we're assuming that we're actually inserting at a random location between k and k plus n.
Is it pretty uncommon, this history independence and randomized algorithms for data structures?
It has been studied a lot for, like, as far as I know, it hasn't been used as a tool to get a faster algorithm before, but it has been used as a goal in itself, like for hashing and B trees and other things like that. People have shown results like we can match the state of the art.
Or hashing, or data structure options that use hashing, they can be made history. I guess it depends what you mean by.
What I mean by hashing, or
No, I think I know what you mean by hashing, but those algorithms.
there are some results in the literature that say like I can match the state of the art while also having the property of history independence.
Great, thanks.